Okay, y'all, this is last video, video D in Unit 5. Okay, so what you're going to notice is we just finished sampling distributions for proportions, and now this is sampling distributions for sample means. And so some of it's the same, some of it's a little different. We will not always have some proportion or some probability that we're looking for. We might just be looking for the means or standard deviation. Now, you're going to want your formula sheet, just kind of a little review. So this top part here is sampling distributions for proportions. So here's when we did everything for proportions, and then right underneath it, sampling distributions for means, and then our formulas that deal with our means. Okay? All right, so just a little review. When we're dealing with proportions, we're dealing with categorical data and means. Remember, when you think about means, it might just be it says the average of something. So a little vocabulary here. Remember, our parameters are coming from our populations, and our statistics are coming from our sample. So when we did this in Unit 6, or Unit C, the one that we just finished, we said that our proportion was P. And we said that our sample proportion is P hat, one single proportion. So our sampling distribution mean was when we had the mean of P hat. So the mean of the population of all of our different samples. And then our standard deviation was sigma of P hat. So we took our sample, and from our sample we did simulations. We took the average of those simulations to get our mean, standard deviation of those simulations to get our standard deviation. Okay. Now, when we deal with mean, we have two things going on. So with population, we used mu for our average, and we used sigma for our standard deviation. And these were from our population. Okay, now our sample statistics, for mean we had X bar, and for standard deviation we just used S. So if we look at the mean here of our population based on a sample, remember these are sampling means, we would have mu of X bar. Makes sense, right? The average of all of our different samples. And then we have the same thing, sigma of our X bar gives us our sampling distribution standard deviation. Okay, so let's talk about this. We are looking here when we decide to give some descriptions, and for our sampling means, we're looking for three things. It has to be random, it has to be independent, and we're looking to see if it's normal. So same things that we did for proportions. So as long as the sampling method is random, then our mean is an unbiased estimator. So we talked about what that means, but an unbiased estimator is going to tell us that mu of X bar is going to equal our population mean, and the same thing that we had here with a proportion. So the mean of P hat is going to give us our probability, or our proportion here when we're dealing with just a proportion. So probability statement and our mean average are going to both give us unbiased estimators if we're using a random sample, so an SRS, or random selection with an experiment. Okay, we need it to be independent, so when sampling, we have to make sure that we follow the 10% condition. And so that's something that we're going to continue to look at here to make sure that it's independent. Now, here's something that's different. So when we're talking about sample means, we do not have large counts. Now, here's why. If we look at what our large counts formula is, it's our sample size times our proportion, and we know that that value has to be greater than or equal to 10, or sample times our failures, oops, this is 1 minus P, has to be greater than or equal to 10. Well, when we're dealing with the mean, we might not have a proportion. So we only use for when we're dealing with probability or proportions. We'll not use these when we're talking about just sample means, okay? We're going to talk about normal curve looking something different in our central limit theorem. So if remember, we talked about central limit theorem, and central limit theorem tells us that when the sample size is sufficiently large, the sampling distribution of the mean of a random variable will be approximately normal. Now, that's not new. And we said that. We know that it's normal based on our sample size. Now, what we did is we did this based on our large counts with our proportions, right? So when we're dealing with a sampling distribution probability or sampling distribution of a proportion, we used long counts with our probability to determine if our sample size was sufficiently large enough to make this approximately normal. Okay, now here's what's different. The central limit theorem requires that the sample values are independent of each other, and that n is large. Now, what happens when we don't have these things? And that's where we're at now when we're dealing with a mean. If the population distribution is normal, so if it tells you in your statement that the population is normal, or both populations are normal if we have a difference, then so is the sampling distribution of X bar. And here's the important thing. This is true no matter what the sample size is. That's why up here we don't have large counts with means. Now, this only works with means. Okay, now, if the population is not normal, so let's just say that it tells you that it's skewed right, or we have no data. Sometimes it'll just tell you, here's your mean and here's your standard deviation, and we don't know anything about what that distribution looks like. So if it doesn't say anything, so if we have no data, or if it tells us that it's not normal, then the central limit theorem tells us that the sampling distribution of X bar will be, this is the important part, will be approximately normal in most cases if n is greater than or equal to 30. So this is kind of a new thing. So CLT tells us it will be approximately normal if n is greater than 30. So personally, I don't think 30 is a very big sample size, but they have determined that n being greater than or equal to 30 will give us an approximately normal sampling distribution of a mean. Okay, so very important. This is completely different than what we had before. What we had before, we had to go up and we had to test this value to make sure that it was going to be normal, and now we don't. All we have to know is that our sample size is greater than 30. Okay, so let's put this in a little chart just so we can compare this a little bit. So shape. So again, we know that the shape is going to be approximately normal if we have one of two conditions. One, if the distributions are normal. And this goes for any sample size. Now, if we don't know anything about the distributions, then by CLT, our central limit theorem, we know that if our value of our sample is greater than 30, we can assume a distribution that's approximately normal. So two conditions. If the distributions are normal, then we can say it's normal. If the central limit theorem, if our sample size is greater than 30, we can assume that the distribution is normal. Okay, our center. So when we have our center is going to say that the average of our sample, so mu of X bar, is going to equal our mean of our population. And that is true as long as we have an SRS. So random assignment or random selection. Okay, so our spread, we know our spread is our standard deviation. We have a formula for that, and our formula for the standard deviation of X bar is going to be sigma over the square root of our sample size, n. Okay, now this is true whether we have a difference or just a mean. We're going to use that for a difference or a mean. So either way, we're going to have this. Now, what do we have to know here? So we have to look at independence So independence is going to tell us what we need to know about our standard deviation. And so here we would say that we're still looking at the 10% condition. And that is that our sample size is less than or equal to 10% of our total population. So this doesn't change. Now, this is true only when sampling, not experiments. Okay? All right, so let's practice this. Now, what you're going to notice, if you go back at lesson A, the very first lesson that was in this unit, we have the same exact problem. The difference is that for that problem, what we're looking for is we're looking for a mean of one girl. So we had a mean of one girl, so because of this, we can go directly to our normal probability distribution. So we don't have to do a sampling distribution because it's only one girl. Now this says, suppose the heights of young women are normally distributed with a mean of 64.5 inches, standard deviation of 2.5 inches. What is the probability that the mean height of a simple random sample of 10 young women is greater than 65 inches? Okay, now we're going to do everything the same that we had previously. So first thing that we're going to do is communicate, and then we're going to create, and then calculate and conclude. So our 4 steps are all going to be the same. So if we look at this first one, communicate the parameter in the context of the problem, write down the probability that of what you were trying to find. So here I know that my mean, so it says what is the probability that the mean height, so I know I have a mean, and this is going to be the average height of a young woman. Okay, what is the probability that the mean height of an SRS is greater than 65 inches? So what I'm looking for, the probability that the mean height is greater than 65 inches. That's what I'm looking for. So now we're going to come down here and we're going to do our create. So I want to look at all 3 things. So the first thing that I have to come up with is this random? So random's going to give me my mean. So is this random? It tells me right here I have an SRS. So yes, it's random. So because of that, I know that my mean of my sample distribution is going to be 64.5 inches. Next thing I'm looking for is independence. So independence is the next thing. So to check independence, I'm looking at the 10% condition. So this says here that I have 10 young women, and I'm going to assume that this is 10% of this big N, which is all young women. And so we've got millions of young women, so I'm going to assume that my sample size is less, so I'm good on that. Okay, so because I've got this, now I know my sigma of my X bar. So my formula of this is going to be my standard deviation. So here's my formula that I'm going to use up here. So my standard deviation is 2.5 inches divided by the square root of my sample size, and my sample size here is 10. So if I plug this in, I have 2.5, divided by the square root of 10, which is 0.791. Okay, now let's talk about this because this is an important concept. So this value here is 0.791, and my standard deviation that I had here is 2.5. So one of the things that's important is that the means are less variable. Than the individual data. So because of this, you're always going to have a smaller standard deviation. Now think about this. This makes sense. If you had one sample or you had a sample of 3 people, your standard deviation is going to be much greater than if you have a large sample. And that's all this is saying. So when we're dealing with means, we're going to have less variability in our standard deviation. Okay? Last thing we have to check here is this normal? All right, so if we look at this, it says, suppose these women are normally distributed. So here's what I have. Because the population distribution is normally distributed, the sampling distribution is also normally distributed. Okay, so what I can assume here is that this sample size is going to be 64.5, my normal distribution, and my standard deviation of 0.791. So I'm going to be able to use this in my calculations. Okay, so let's go here. Sorry, it's on the next page, but calculate the probability converting your data to a z-score. So nothing new. And I'm going to get rid of this. Draw the curve as optional. Don't always draw the curve. Okay. So again, my problem statement was the probability that the mean is greater than 65. Okay. So what I know here is that X bar is normally distributed, and we just wrote that down, 64.5 and 0.791. Okay. So probability that Z is greater than, let's see, 65 minus 64.5 divided by 0.791. Let's see what this is. Let's see, 0.6321. Okay, so I'm going to draw my curve. I know it's normally distributed. This is 0. This is 1. So my value here is going to be 0.6321, and it's the values that are greater. So it's this direction. And now if I plug this into my normal CDF, my lower bound is going to be 0.6321. My upper bound is infinity. And my mean is 0, and my standard deviation is 1. So what I get here is 0.2637. Okay, now last step is my conclude. What do I want to say? So my conclusion here, the probability that the mean height of an SRS of 10 young women BEIN being greater than, it's probably not very good English, being greater than 65 inches is 0.2637. Okay, let's keep going. All right, this next one. A particular restaurant chain is suspected of undercooking its burgers. The restaurant claims its burgers are cooked to a medium doneness with an average internal temperature of 160 Fahrenheit, standard deviation of 5. For the question that follows, assume the restaurant's claim is accurate and the distribution of internal temperatures follows a normal distribution. Okay, what is the probability that a single randomly selected burger is cooked to an internal temperature of 158 degrees or less? Okay. So here's what I have. This is asking, what is the probability that a single burger is going to be cooked less than or less, so equals 158. Okay, now what I'm going to say here is X is a single random cooked to an inch. So this is our burger temp. Okay, so what I know here, it tells us that it follows a normal distribution. So that tells me that X is approximately normal. It has an average temperature, so a mean of 160, and a standard deviation of 5. So if I go to convert this to a z-score, so z is going to be less than 158 minus 160 divided by 5. So if I plug this in my calculator, I get that z is less than negative 0.4. So here's my normal distribution, negative 1. So negative 0.4 is going to be right about here. And I want to know less than that. So is my burger undercooked? So when I plug this in, normal distribution, this is going to be my negative infinity number. And I'm going to go to negative 0.4. And this is 0.3446 is my value. So what does this mean? The probability that a single burger, which is randomly selected, is cooked 158 degrees or less is 0.3446. All right, so now it says a secret shopper comes in at random times throughout the day to test the internal temperature of the burgers. They select an SRS of 25 burgers. Okay, so now we've got more than just one. So we're single, now we have more than one. And calculate the sample mean. What are the mean and standard deviation of the resulting sampling distribution? So I'm going to look at this for a second, just because I think this is good practice. So is this random? Remember, random gives us our mean, and it tells us that's an SRS. So we know it's mean. We know that this is true. So here, this can tell us that our sampling mean is going to be the same as our sample mean, which is 160. So here our population, I think I said sample, but our population mean is 160. So since we used an SRS, we can say that the average sample mean is 160. Is this independent? So we have 25 burgers, and that is going to be less than or equal to 10% of all burgers cooked. So we're going to assume that they're going to cook more than 250 burgers, okay? Which, if it's a fast food restaurant, that's probably pretty true. So now I can go in here and I can say the standard deviation of this sample is going to be 5, which is my standard deviation, over the square root of my sample set, which is 25. So this is 5 over 5, so my standard deviation is going to be 1. And then last, I need to know, is this normal? So it tells me in here that it is normal, so normal is given. So I know that this is true. So the question says, what are the mean and standard deviation of the resulting sampling distribution? So my mean is going to be 160, and my standard deviation is going to be 1. All right, and I think there's a part C to this. Yeah. Okay, so part C. The secret shopper in B obtains a sample mean of 158 degrees Fahrenheit. What's the probability that the random sample of 25 burgers produces a sample mean of 158 degrees or less? So assume all conditions. We just did that in part B, so we're not going to do that again. So now we have the probability that our sample mean, that's what this is. So this is my sample mean, is less than or equal to 158. Okay, and we can convert this now to our z-score. So 158 minus 160, and our standard deviation was 1. and this is going to give me a z-score. I don't even need to plug that in. Almost did that, which is crazy, of -2. So what does my distribution look like? 0, -1, -2. So here is what I care about. Okay, so now I'm going to plug this in, and the value that I get here, so inverse norm, oh sorry, norm, and this, I'm at -2, and this tells me the value is 0.0023. Okay, so why is there a difference in the results in part A and part C? Explain why one is more likely to happen than the other. So here's what I have. So part A, I had the probability of one sample. It was just one burger. And we said that the probability of that one burger being less than or equal to 158 was, let me look back over here. Oh, it's on the other side. 0.3446. Now, in part C, the probability of a simple random sample of 25 burgers, right? And we said that that value here was equal to 0.023. Well, if you look at this, there's a big difference here between these two values. So here we said that our standard deviation was 5, so we had more variability. And here we said our standard deviation is 1, so this is less variability. And so because of this, we have a lower probability. Now, to me, I have much more confidence eating in that place with this simple random sample of 25 versus this one burger that they picked, right? So that's why it's important to look at this, because we have a much lower probability that our burger is going to be undercooked when they did this random sample of 25 burgers. So that's why statistics are so important. So we're going to throw in this sampling difference. So here we just have a difference of means. And this is not anything different, right, that we've been doing. We've been doing this with proportions. And so we have that X bar of sample 1 is the mean from the first group, and X bar of sample 2 is the mean from the second group. So what do we know about our shape? Well, like everything else, our shape is going to be approximately normal. And we always have these conditions, so it's going to be approximately normal as long as n sub 1 is greater than or equal to 30 and n sub 2 is going to be greater than or equal to 30. And this is used for based on CLT. So we know that both of our sample sizes have to be greater than 30, or both are normal, if it tells you that they are normally distributed. And then our sample size doesn't matter. Okay, so our center, what happens when we have a center? This is not anything new. So our center of X bar 1 is going to be the center 1. And our center of X bar 2 is going to be center of 2. And the way we would read this would be this is going to be the center, which is the mean. And then this is going to be, this tells me I have a sampling distribution. And this 2 right here is going to tell us that this is the second group. So it just kind of breaks it all down, but then we can summarize this. So we can say that all of this happens, we have mu1 minus mu2. All right, now we know we've been dealing with this, this happens as long as we have an SRS or random assignment. And I know you're getting so sick of writing that, but that's good. Then you won't forget. All right, so distribution. So our spread, our standard deviation, what do we have? So we just said that when we have the mean of one sample, this is going to be standard deviation of that sample over the square root of the sample size. And if I have x bar of 2, this is going to be the same thing. Now, what we know, and I'm going to do a little bit of math here, and then you don't have to worry about showing this again, because this is on your formula sheet anyway. But we know that when we have a standard deviation of two things, and whether we're adding them or subtracting them, it doesn't matter. We always take the standard deviation of the first thing and square it, and we take the standard deviation of the second thing and we square it. Okay? But look what happens. If we take this and we plug it into the parentheses right here, what you end up happening is in your denominator, you have the square root of something squared, right? Here, let me just write, I'll write the second one. Square root of n squared. So we have a square root of something squared. So this formula actually simplifies to sigma 1 squared over n1 plus sigma 2 squared over n2. Now, remember, I'm going to just write this over here, is when we have the square root of something squared, this is always our variance. So it might tell you the variance, or it might give you the standard deviation and you have to square it. So think about that. If it tells you the variance, it's already squared, and so you just plug that value in. Okay? Now, this, of course, is going to happen if both samples, and this is assuming that you're sampling, both samples satisfy the 10% condition. And we know what that is. It says the first sample is 10% of the total population, and the second sample is 10% of whatever that population is. So if we're dealing with men and women, we would have different overall sample sizes. Okay, let's do an example problem here. This says, a study is conducted to compare the effectiveness of two study techniques, A and B. So we have two things for improving test scores. For technique A, a random sample of 80 students. I'm just going to write all this stuff down. So for technique A, we have a random sample of 80 students, and we have an average score. So average score of these students is going to be 85, with a standard deviation of those students being 10. For technique B, we have a random sample of 100 students. A mean is going to be 82, and a standard deviation of 8. All right, so what am I looking for? Calculate the probability that the difference in the average scores between A and B is greater than 4. So what am I looking for? So if I go down here, I'm going to write all this down just so we have this. So if we look at our communicate, you don't have to write this down, but it kind of helps you keep your 4 C's in line here. We want to know the probability that the difference in the average scores. So mu x bar A minus mu x bar B is greater than 4. That's what I'm looking for. All right, so now I'm going to look at my conditions. So first thing is it random? And remember, random gives me my mean. And they're both random. I have two SRSs. So I can say that the mean of A minus the mean of B is going to be 85 minus 82, which is equal to 3. So the difference in my mean is going to be 3. Next thing I have to check is my independence. Independence is going to give me my standard deviation. So for independence, what I'm looking for on this one is my population size. So I had 80, and I would say that that is less than or equal to 10% of all technique A. And then the other one would be 100 is less than or equal to 10% of all technique B. Now, here's what I don't know. I don't know. Is this happening at a university? Is it happening where? Is it happening across the country? You know, all of this, where is this happening? So I'm going to assume, and I'm just going to say, assume large population sizes. And actually, now that I think about this, should be 80 is less than or equal to all. I'm just going to say this is all people. Not people that are doing that technique. That's the 80 and the 100. So this is going to be 10% of all people. And so that, of course, that does give me a large population size. So now I look at standard deviation of x minus b. Now I have standard deviation. I don't have variance. So what that's going to look like is 10 squared divided by my sample size of 80 plus 8 squared divided by my sample size of 100. Now, if you remember, here's my formula. It's also on your formula sheet. Standard deviation squared over your sample size plus standard deviation of your second population squared over that sample size. So that's where this comes from. And when I plug this in, I get 1.378. Okay, so last thing here is I'm checking to see if this is normal. So I'm checking my shape. All right, so what does this say up here? It says improving test scores, technique A, random sample, technique B, random sample. Calculate the probability that the difference of the average scores between A minus B is greater than 4. So what do I know about normal? So it doesn't say anything about the distribution. So I have to know by CLT, is my sample size greater than or equal to 30? So I have 80 is greater than or equal to 30, and I have 100 is greater than or equal to 30. Therefore, I can say that it's normal. All right, so now I'm going to go down here to my calculate. So what I know now is that I'm approximately normal with a mean of 3 and a standard deviation of 1.378. All right, so if I want my probability, and I'm just going to write this, x bar A minus the mean of x bar B, and I know that I want this greater than 4. When I calculate my z-score, I'm going to have 4 minus 3, or 1.378. Divided by 1.378, it's 0.726. Okay, I drew my little graph there, so now I'm going to go in here and do normal CDF. My lower bound is 0.726. My upper bound is infinity. And I get that this probability is 0.234. So last step here is going to be my conclude. And what I'm going to say is the probability that the difference in the average scores of technique A minus technique B is greater than, what do we have? 4 is 0.234. The probability that the difference in average scores of technique A minus technique B is greater than 4 is 0.234. Okay, sorry, I know that was a long one.